Looking at some other problems here in our integration strategies section, I think you'll find number 27 to be an important type of problem to understand. Notice we have x to the 1/2 over x to the 1/3 plus 1. There's a trick to this one, and it's difficult to see in the first step. As soon as I see that plus 1 in the denominator, my goal is to try to force a u squared plus 1 in the denominator, because anytime we can get that expression in a problem, usually good things happen, such as inverse tangent and stuff like that. So in this one, if I'm thinking of that, I can say, well, I know that that's x to the 1/3. If I'm going to let that equal u squared, then that means u is going to equal the square root of that, or x to the 1/6. So I'm using the substitution to let u squared equal x to the 1/3. So u is equal to x to the 1/6. Now that's going to give me the derivative of u. du is going to be 1/6 x to the negative 5/6 times the derivative with respect to x. Now I need to replace dx in the problem, so I went ahead and solved for dx, and I can say, well, if du is equal to this in terms of dx, then dx is going to equal 6 times x to the positive 5/6 on the right hand side times the du. Okay, now I look back up at my problem and I can see, well, x to the 1/6 is u, so x to the 5/6 would have to be u to the 5th. So I'm going to be able to substitute in the place of dx in the problem. Notice the dx becomes 6 u to the 5th du right here. The x to the 1/2, that's just going to be x to the 1/6 cubed, so that's why you can say I'm replacing that with the u cubed there, and that's what I'm showing right here as well. My denominator, u squared plus 1. Now I went ahead and factored the 6 out after I put it all in terms of u, and my numerator would just be u to the 8th du over u squared plus 1. Anytime your numerator is of greater or equal to degree than your denominator, you can go ahead and use long division. I could have done that in the first step, but it's kind of tricky with your fractional exponent. It's a lot easier to do now, so I'll go ahead and do the long division. U squared plus 1 divides into u to the 8th. I know u to the 6th times. I get u to the 8th plus u to the 6th. I subtract that out, leaving me a negative u to the 6th. Then I say u squared goes into negative u to the 6th, negative u to the 4th times. I get negative u to the 4th times u squared is negative u to the 6th. Negative u to the 4th times 1 is minus u to the 4th. Of course, we subtract that group out. We see our u to the 6th terms cancel, and I'll have u to the 4th left over. U squared divides into u to the 4th, u squared times u squared is u to the 4th. U squared times 1 is u squared. Now we subtract that group out. My u to the 4ths cancel, and I'm left with a negative u squared. U squared goes into negative u squared, negative 1 times. Negative 1 times u squared is my negative u squared. Negative 1 times 1 is my minus 1. Notice, guys, I'm subtracting that out. The u squareds cancel, and I'm left with a positive 1. Now, this actually makes for a gorgeous problem now, because I can say, okay, this original integrand, which is equal to this in terms of u, now is going to be all of these terms, which they're all extremely easy to integrate. It's just power rule for each one of them. But now, the other one, I can say, well, I'll have plus 6 on the integrand of what's left over divided by what you're dividing by. So in other words, 1 over u squared plus 1. And then that we automatically recognize, well, that's just an inverse tangent of u there. Gorgeous. I went ahead and integrated every term using the power rule, the last one using the inverse tangent derivative. And then once I got my answer in terms of u, the only next step was to go back in and plug it in terms of x. I know everywhere I have a u, I'll put an x to the 1/6, and that's where I got this final answer there. Pretty nice problem there. Again, I think you'll see something like it on the online assigned problems. The next one here. And again, I'm trying to do ones that you'll see assigned online. if I give you the integral of x squared natural log of x dx, as soon as you see a natural log in there, especially as part of a product, you should automatically be thinking integration by parts. So you let u equal the natural log function, dv equal everything else, which is x squared dx. Then I can say, well, clearly the derivative of the natural log is 1 over x. The integral of x squared is going to be x cubed over 3. And so now I can say, then my answer for my integral is equal to u times v. U times v, I'm getting 1/3 x cubed natural log of x minus the integral of v du. That's going to be 1/3 x squared. Notice I went ahead and factored out the 1/3 on the integral of x squared dx. So now I can say, well, I know that the integral of x squared is, again, x cubed over 3. Multiply that by another 1/3. That's why I got minus 1/9 x cubed plus my constant of integration. Done. That was actually a quick one. Another one through here, and again, I'm trying to do the ones I think you'll need to know. If I look at 39 with you, a lot of people would really struggle with this one. In a lot of ways, it's very similar to what I did here in 27, though. You'll notice the first step I did in 27 is I let u squared equal x to the 1/3, so u is x to the 1/6. In this one, I'm going to let u equal that square root of x. And so if I let u equal the square root of x, think about how this is going to help this problem. Well, then du, the derivative of u is going to be 1/2 x to the negative 1/2 with respect to x. I need to be able to substitute in for dx. I went ahead and solved for dx here. I'd need to multiply by 2 and by x to the 1/2 on both sides. So I can say dx is equal to 2x to the positive 1/2, or 2 square root of x du. And then the root of x we know is u. So then I can say, well, then this is just 2u du that I can replace for the dx. So inside my problem, if the square root of x is u, then x is going to equal u squared. That's where that came from. X is u squared. We've already discussed dx is 2u du. All over my denominator of u squared minus 1. Just like in number 27, I can go ahead and factor the constant out. My numerator is a u cubed. So then I have u cubed over u minus 1. Instantly you get to that point and you say, hey, numerator's of greater degree than the denominator. You should go ahead and use long division. I discussed the long division in the earlier problem number 27. So this one, I'll just show you the long division there without going into it. But then the nice thing about this is it's leaving me with u squared plus u plus 1 for my answer with a remainder of 1. So then this integral, again, I still have the factor of 2 out front on the integral of u squared plus u plus 1 plus the remainder 1 over u minus 1. And then again, this is nice because every single term, these are all integrable by the power rule. The last one, anytime you see the derivative of the denominator in the numerator, the answer is the natural log of the absolute value of the denominator. So each one of these terms has a very basic integration rule that applies to it. I'll get u cubed over 3 plus u squared over 2, u to the first over 1, natural log of the absolute value of that denominator plus c, all of it times 2. The only thing after that, of course, is everywhere you see a u, you have to replace it with a root of x. So I'd have the root of x cubed, or, yeah, that's how I wrote it, root of x 2/3 root of x cubed plus the square root of x squared is just x, and then the 2 canceled out with the 2 that I was multiplying by. Then I would have 2u becomes 2 root of x, and then the 2 natural log of the root of x minus 1 plus your constant of integration. It's a pretty good problem there. Now you're thinking, hey, you want to see a harder one. That one wasn't hard enough. Alrighty, let's look at 47. And actually, this one's not too bad either. Because, again, at the very beginning of the problem, you should automatically know what's done in it. You see a natural log. Instantly, when you see a natural log, you should be thinking integration by parts. So the only part of it was the natural log, and then the only other existing part was the dx. So that's the only way to break it apart. I'll say You can't take the natural log without putting the argument in it, so u has to be the natural log of x squared plus 9. dv has to be dx. I take the derivative of the natural log. Derivative of every single logarithmic function in existence is 1 over what's inside the logarithm. The numerator becomes the derivative of what's inside the logarithm, so the derivative of x squared plus 9 is 2x with respect to x. So here's my du. My v is just the integral of 1 with respect to x, which gives me x. So now I would say, okay, my integral answer is u times v. Well, that's the x times the natural log of x squared plus 9 minus the integral of v du. Here's v, here's du. Notice I'm pulling that 2 out front, and then I would have x squared over x squared plus 9 with respect to x. Yet again, we see a problem where the degree of the numerator and denominator are the same, so you can use your long division. In fact, instead of saying you can, you must. So I'll say x squared plus 9 divides into x squared one time. When I do it that one time, of course, I'll get an x squared plus 9 down here that we're subtracting out. The x squareds cancel. You'll be left with a negative 9. So what I know this last group is going to break down into is just the integral of 1 dx, and then I had 9 left over. So notice that 9 that I had left over was a negative 9. So that negative 9 came out and multiplied the existing negative 2 that would have been in front of it. That's where that plus 18 came from. And then I have 1 over x squared plus 9. And then I just recognize, hey, this is the inverse tangent substitution formula. If I have 1 over x squared plus a squared, it's going to be 1 over a inverse tangent of x over a. So this is x squared plus 3 squared. So I said that would be, the inside part would be 1/3 inverse tangent of x over 3. The 1/3 multiplied the 18 to give me a 6. Of course, the 1 integrated to be x, so I have the minus 2x for that term, and we were already done with the first term. Now, if you wanted to go the long way in this one, you could have also used substitution and let something like 9u squared equal x squared, like we had to do back in chapter 5 there. But now, since our problems already contain other parts, and that's just one component of our problem, it's probably wiser to use your tables or just your memory. That one might be one that you just have memorized already by now. Last one here. I wanted to look at number 53 with you. This is a gorgeous one. And yet again, you see long division is an important component in it. As soon as you see the first step, degree of the numerator is greater than the denominator, I divide the denominator into the numerator. It goes x times. I get x to the 5th minus x. I subtract that out. The x to the 5ths cancel. But then I'm left with a positive x for the remainder. So you'll notice I went ahead and I broke my original integral down and said, well, it's just the integral of x dx plus the integral of x over x to the 4th minus 1. Now, this second one, as soon as I see that x to the 4th minus 1, I can see that this can be factored really nicely. That's what I did right here. I said x over x to the 4th minus 1. X to the 4th minus 1 is a difference of two squares. You'd say x squared plus 1 and x squared minus 1. But x squared minus 1 further factors to x plus 1, x minus 1. Now that you have your denominator completely factored out, you have to use the method of partial fractions, section 7.5, to break this apart. Over every irreducible quadratic, you need a linear numerator, so I have the ax plus b over x squared plus 1, plus a constant numerator over each linear denominator, so c over x plus 1, plus some constant d over x minus 1. Now I multiplied by this least common denominator of all three of these terms on both sides. On the left, I would just get an x. On the right, you'd have your ax plus b times the two linear factors. You would have c times both the irreducible quadratic and the linear factor x minus 1. And you would have d times the irreducible quadratic and the linear factor of x plus 1. Now, as a matter of trying to solve out for some of the letters, Anytime you can make a denominator of any of these fractions equal to 0, you're going to be able to solve for a variable. So here, if I let x equal 1 or x equal negative 1, I know I can solve for a variable. So first of all, I let x equal 1 here. If I let x equal 1, I can see that a and b cancel out. I can see that c cancels out. I'll be able to solve for d. When x is 1, your left-hand side, x is 1. Your right-hand side, you're going to have d times 1 plus 1 times 1 plus 1. So obviously it's going to be d times 2 times 2. I get 4d is 1. So I know d is 1/4. Now, when I let x equal negative 1, my left-hand side is a negative 1. And I can see that your ax plus b term would cancel out and be multiplied by 0. Same thing with d. It's going to have a factor of 0 multiplying it. But now your c term, you'd have negative 1 squared plus 1. That's going to be 1 plus 1 is 2. Negative 1 minus 1 is negative 2. I'll get c times negative 2 times positive 2. So in other words, negative 4c is equal to negative 1. C is also going to be positive 1/4 because you'd have a negative over negative there. Now, in order to determine A, what I did is I said, well, since I already know C and D, and I know A is going to be the coefficient of an x cubed term, I'd have ax times x times x. I know C is going to be the coefficient of an x cubed term, I'd have cx squared times x. And I know D is a coefficient of an x cubed term, I'd have dx squared times x. I can see B will never be able to be a coefficient of an x cubed term. It can only at most be the coefficient of x squared. So if I look at the coefficients of x cubed, on the left-hand side, you don't have an x cubed, meaning its coefficient is 0. On the right-hand side, your coefficient of x cubed would be a plus c plus d. We already know c and d are both 1/4. So I know a plus 1/2 has to equal 0, which leads me to the solution that a is equal to negative 1/2. Then I looked at my constant to determine b. I know that the constant on the left-hand side, there is no constant on the left-hand side, so it's a 0. B is going to have is going to be multiplied by a factor of negative 1. So my constant in that term, the expression without an x term, is just going to be negative b. Same thing for c, it would be multiplying a negative 1, so I'll get negative b minus c, and then I would have plus d, because d is going to be multiplied by 2 positive 1s. So then I can say negative b minus c plus d must equal 0. So negative b minus c, which is minus 1/4, plus d plus 1/4, those two clearly cancel each other out. You just get negative b is 0 in this case. So now, when I go back to my problem, I can say this original integrand, we already know that the first one's easy to integrate, the integral of x dx, that's just going to be my 1/2 x squared. But the rest of this, I had to break this apart with the partial fractions. The first partial fraction I know is going to be plus the integral of ax plus b over x squared plus 1. So that gives me negative 1/2 x plus 0. Notice what I went ahead and did. Instead of putting the negative 1/2 in with the x, I went ahead and moved it to the outside. Now, the second term, you have plus c over x plus 1. Well, plus c over x plus 1, I factored out the 1/4, 1 over x plus 1 on the inside. The last one, d over x minus 1, 1/4 over x minus 1. Again, I brought the 1/4 out in front and had 1 over x minus 1 on the inside. Then you can say, well, these last two are super easy. Anytime you can see the derivative of the denominator and the numerator, it's going to be the natural log of the absolute value of the denominator. These two are no problem. This one, slight problem. I can say, again, it is a natural log. The reason I know that is because anytime I can see the derivative of the denominator in the numerator, then the answer is the natural log of the absolute value of that denominator. But in this case, we know that that x squared down there, you would need a factor of 2 in the numerator, but if you do that, you'd have to multiply the outside by 1/2. That's precisely what I did when I went from this step to this step. So I have 1/2 x squared, the integral of the first one. This is going to be minus 1/4, and then the derivative of the denominator is in the numerator, thus it's the natural log of that denominator. I didn't need the absolute value since x squared plus 1 is automatically positive anyway, plus 1/4 natural log of x plus 1 inside of an absolute value, plus 1/4 natural log of x minus 1 inside of an absolute value. Of course, plus our constant of integration. And all I've done from this step to this step is I just condensed my 3 logarithmic functions. We know that it's going to be, since they all had coefficients of 1/4, I said 1/4 the natural log. The 2 positive terms have factors in the numerator, so x plus 1, x minus 1. My denominator had the 1/4 that was being subtracted, so that means that that term inside the natural log goes in the denominator, so I divide by x squared plus 1 inside of there. And I have a very nice answer, and like you see, I really liked that last question there. And never fear, you'll have one to work like it very similar online, and I hope you'll have fun with it and be successful now after looking at this with me.